friend. Today we're going to talk about the concept of sample mean and sample standard deviation, and how those two works. And we will also implement that in Python whenever we get the chance. So let's start with the mean. So what is the mean? The mean is pretty simple. The mean um, is pretty much an average. So you take a few data points. Okay, you add them up and you divide by the number of data points. So let me phrase this as an example. So usually you will see um, the mean expressed as y bar or x bar. It really doesn't matter, but you're gonna have 1 over n times summation of um, each data point, and the data point can go from 1 to n. So let me explain you each part of this equation. So yi, these are the data point. It can be 2, 3, 4, and 5, right? And then you do a summation of these values. Okay, you do a summation of these values. Okay, what does the summation means? Summation means that you gonna have to uh, sum 2, 3, 4, and 5. Okay, and then you divide by n. So one n is the number of elements. So you have 4 elements here, so you're gonna have to divide by 4. Okay, so this is pretty much what this means. So if when you do your math, you end up having 2 plus 3, 5, 5 plus 4, 9, 9 plus 5, 14. So you end up having 14 over 4. And you can, of course, use your calculator to achieve that, to get the final answer. So this is what the mean is. Now, there's what's called the sample mean and the population mean. So the sample mean is what we just calculated. Which is y bar. And what is the difference between y bar, the sample mean, and let me write sample mean, and what you call mu, which is the population mean? The difference is the population mean is always unknown. Why is it unknown? Because you will never get the true population mean. It's never a correct answer. The only way you can read the population mean is to get some type of sample, which is representative enough of the population, and attribute the value of the sample mean to the population mean. So that's the only thing you can do. Okay, it's very unlikely for you to know the exact value of the population mean. So this is the main difference between population mean and sample mean. All right, so let's get to the standard deviation and the variance. Let me erase all this. Um, the variance is pretty much it's pretty much pretty simple to understand. It's a distance. It's a distance between each data point and the mean. So we found out last time that we have our mean, our sample mean as 14. And let me make an assumption here. Say for instance, we have our sample mean as 5. Okay, and we try to find the variance. The variance I'm gonna call the sample variance, of course. I'm gonna call it s squared. This is nothing else but 1 over n minus 1 summation of each data point minus the mean, and that is square. And the data point can go from 1 to n. Okay, so let me explain each part. The reason why the variance is also an average, people talk about the variance as an average, because you also divide by a certain number of elements, which is represented here, but you also, looking at some data point. And the data points, let's go back to our previous example. So we have data point 2, 3, 4, and 5, correct? And we want to calculate the variance. So we're going to have to calculate a difference, okay? Each difference, you're going to have to calculate 4 differences. each difference will have, if I use the right color, each difference will have uh, 2 minus 3 raised to the power 2, and then we're going to have to add 3 minus 3. No, not 3 here. It's supposed to be 5, correct? So it's going to be minus 5 raised to the power 2, and 3 minus 5 raised to the power 2, plus 4 minus 5 raised to the power 2, plus 5 minus 5 raised to the power 2. Having said that, you use your calculator to calculate this each quantity, okay, that you raise to the power 2. When you add them up, you divide all of these by the number of elements. So here you have 4 elements, which you subtract 1, and you have um, 3 elements, okay? So this is how you calculate the sample variance. Some people will argue that it should be divided by n, okay, and others will divide it by n minus 1. But really, don't worry too much about the reason why you should divide by n or n minus 1, because this is more into getting more into theory. But in most books you will see n minus 1. Okay, so just follow what your textbook said. But this is pretty much how you apply the formula of the variance. Now the sample variance in itself needs the calculation of the sample mean. Okay, and it's pretty much a distance. So you're trying to measure the distance between the mean and each data point. So we're trying to find out how far is is the average data point from the mean. That's pretty much what the variance is. So there is another quantity that you may have heard of, which is called the standard deviation. And the standard deviation is pretty much the square root of the variance. So once you find your variance, all you have to do is you can calculate your standard deviation as the square root of your variance. Remember, your variance is always s squared, and the standard deviation is the square root of s squared. Now, we keep talking about sample, okay? We keep talking about sample, but when it comes to population standard deviation, you will see this sign, which is sigma square, okay? This quantity, okay, this variance, this is called the population variance, and s squared is called the sample variance. And again, it's the same concept because you would never know the population variance, and you will have to find a you know a representative sample, to be able to draw your conclusion and assign your conclusion to the population variance. So this is how it works, and you're gonna have to run some test statistics and so on and so forth. All right, so let's talk about the conclusion here. Where am I getting here? Um, there is a concept when you get to many data. So we have worked with 4 data points here, but what if you work with many data points? Okay, what if you work with many data points? You may be tempted to to estimate to do some estimation of how your population should look like. Okay, and a very use good use case will be that when the higher the population, okay, when your population grows, all your mean and sample variance can always be approximated to what's called a normal distribution, because when your population is small, you have 2, 3, or 4 data points, you may have uh, you know some weird shit because you have 2 or 3 data points. But the higher your population, or the bigger your population, and the more your population tend to have a bell curve. So that what this means is that when you go from 3 to 4 data points to 1,000, 10,000, a million data points, you will almost see something called a bell-shaped curve. So this is called a normal distribution. This is called normal distribution. And from the normal distribution, you can pretty much have an estimate of how your population looks like. So let me give you 3 empirical rules that you can use for that purpose. The first one is that given that you have the mean and the standard deviation, Okay, let me erase actually the first this part. Given that you have the mean and the standard deviation of your population, you can have these the following rules. The first one is that your mean can be um, one standard deviation, your any data point um, contain approximately 68% of your measurement. So that means that um, your mean, which is in the middle, okay, can be um, can be separated by one time the standard deviation, and when it's separated by one time the standard deviation, this is equivalent to 68% of the population. So you have 68% of the population that is covered by plus or minus one standard deviation of the mean. Okay, so let's put 68%. All right, you have a second rule which says that your mean, okay, when your mean is plus or minus two times the standard deviation, then this is equivalent to 95%. And all these are called confidence intervals, okay? And then when you have a population that is three standard deviation of the mean, in some textbook you will see either 99.99%, or I would say close to 99%, or some people will say 99.7%, but it doesn't matter. It's always close to one. So let me give you a small example. Okay, let me give you a small example. So, say for instance, you have a some high school senior, college student senior, and you know that. Let me erase the board. Actually, I'm getting ahead of myself. I was drawing a normal distribution, and I'm stepping back a little bit. I was actually not done. So I have plus minus one time the standard deviation. So this is by 68%. What if you have two times the standard deviation? That will become minus 2 sigma minus 2 sigma. That will cover almost 95% of your population. Okay. So all this will be 95%. And when you have um, plus or minus three times the standard deviation, that will cover what? Pretty much the whole bell curve, okay? Pretty much the whole bell curve. So that's the illustration that I failed to explain you, but I hope you get the point. Okay, so the more spread out um, the number of standard deviation away from the mean, you know, the more the bell curve tend to expand. So that's what I wanted to show you. Now, um, finally, I was going through an example, and I was saying that if you know that if you know your population mean and your population standard deviation, you can actually approximate any type of distribution. Okay, so and I was giving the example of some type of achievement test of high school senior. Okay, say for instance the test score are approximately distributed with an average score of 64 for those high school seniors and a standard deviation of 10. With the empirical rule that we just talked about, we can actually have an approximation or know approximately um, how, if we consider, okay, one standard deviation away from the mean, we can say and conclude that, okay, 64, okay, plus or minus 10, which give us 64 minus 10, that give us what, 54, okay, which is um, the lower bound, and when you do 64 plus 10, that's 74, which is the lower bound. And if you remember, we mentioned that just one standard deviation away from the mean is equivalent to what? 68%. So we can conclude here that 68% of our scores are between 54 and 74 without doing any calculation and without using any calculator. We can have this up. We can be sure that it's around that approximate percentage. Again, this is an approximation, is not exact, but we can say that given our mean of 64 and our standard deviation of 10, we can conclude that 68% of our population range between 54 and 74. All right. How about two standard deviation from the mean? How about 95%? We can also conclude that, hey, this time, instead of just subtracting 10 one time and adding 10 one time, we are going to subtract and add 10 two times to get the lower bound and the upper bound. So what we're going to say, we're going to say 64 minus 20, which is 44, and 64 plus 20, which is 84. So you see, the number of time you add or subtract your standard deviation make your confidence interval bigger. So 95% of your confidence interval here cover test score between 44 and 84. So that's it. I hope that was helpful. I cover in this video the concept of mean and standard deviation. In my next video, we don't have enough time to cover the implementation in Python, but in my next video, I'm gonna make sure I do that. I hope you like this video. If you do, please give a thumbs up and subscribe for more statistic content. Thank you very much.